Okay, this is this is the name of the course. The name of the course is taken from the book. The book is a famous book. It's 20 years old, and it was produced by some professors at MIT. And it's famous because it changed the way that people look at computer programs. Now, the book has become a little dated, so we don't exactly follow all of the book the whole way through. In particular, this used to be the book for a first-year course at MIT. 6001, a famous course based on this book, and it was replaced in many ways. The program that you saw in your first year, How to Design Programs, was designed as a replacement for this book. And there's a famous paper, The Structure and Interpretation of Computer Science Education, in which Felice and the others who wrote How to Design Programs justify why they wanted to replace this book with HTTP. It doesn't change the fact that this is a very good introduction to some more advanced topics than you saw in How to Design Programs. And so we still go with this book. This book's very famous. If you want people to think that you're a cool hacker, you need a copy of this book, and you just sort of leave it around for people to see. Okay, so I've read that book. I've read the Purple Book, and everybody knows it as the Purple Book. It's the book that all the cool people have read and done and been through. And so you'll find that the cool places like Koch or Otto, the places where they use scheme for education, they'll all go with the Purple Book. In fact, at Koch, they go with the Purple Book that they use the terrible version of MIT scheme, which is almost impossible to use, that's recommended in the book, so that that shows how cool it is. And what is the course really about? Well, it's about exactly what it says: the structure of computer programs and what they mean, their interpretation. What do the programs mean? And so we've got this far in programming, going through How to Design Programs and the courses you saw last week, data structures and algorithms and the rest. We've got this far really without thinking too much about what does it mean? What does it mean to apply a function to some parameters? What does that really mean? We've just said, well, you just kind of take the values and stick them in. What does it mean? We all know that maybe the x in one function may not be the same as the x in another function, where we've got two different names. We want two names the same, but in different places. What does it mean, and how do we control that process? What does it mean to say that those two x's are different? They look the same. We will be looking at those sort of things, and we will be looking at how we give meaning. So that we'll be looking at programs as data. So you can, in the process, we will be looking at different ways of looking at programs and smarter ways to program. So you can think about, there'll be lots of cool ways to write programs. To understand programs. Cool ways to generalize programs. What do we mean this? I mean, cool ways to write programs, it means sometimes we're going to write programs which, if you wrote them in Java or in C, would be very long and complicated, and we're going to write them in one line. Okay, so that's pretty cool. We're going to write neat one-line programs, or two-line programs, or three-line programs, where it will be The programs will be big, complicated and hard to understand. We're going to write a neat program which is short and easy to understand. Understanding programs involves, understanding anything involves having some kind of patterns in your mind. When we listen to natural language, when we listen to one another speak, or we read sentences in a book, or we look at a picture even, what we have is we have a set of patterns in our mind that enable us to interpret what we are seeing. Nobody, when you're reading or you're listening to what somebody's saying, actually understands it one syllable at a time. What you do is you have a pattern in your mind and you match that pattern against some templates that you've got, the templates that you've got in your mind. So for instance, if you look at this and read it, what most people see is Paris in the spring. Okay, is that what you saw? But it's not Paris in the spring, isn't it? It's Paris in the spring. But you saw, and I saw, whenever I say it, is Paris in the spring, because we're used to the not being repeated in sentences, and we actually perceive it in that way. We have patterns. We have patterns. We've talked about patterns before. What were the patterns we talked about in the first year? When we were learning how to design programs in the first year, we had some patterns, didn't we? What were those patterns? What were the patterns we had? We learned about a design process and a design method. What were the patterns we saw? And that we kept using over and over again. So we had some kind of, a particular kind of problem. In fact, we had a series of kinds of problems, getting more and more difficult as we went through the first year, and we were applying a design method which got more and more sophisticated as we went through the year. And what sort of patterns were we seeing? Well, can you say that there was one particular type of program that we saw, in a particular stage in Comp 149, 150? So this lesson is being videoed, so this is for the people watching on video. Now, what sort of patterns did we see in the first year? What was there in the design method? What was the design recipe? And how did the design recipe change as we went through the year? Come on, what are the steps in the design recipe for designing a program? Data definition, purpose, contract, examples, template. Okay. And didn't we find that we had kind of different kinds of templates, didn't we? We started off with a template which just said you do something to the parameters for the function. And then what did we have next? We had a template with some conditionals in it. And what did we have after that? What did we move on to after that? Structured data. And then after that, recursively structured data. And we had something like a template which worked on recursively structured data. We said you have to do something to whatever's in that data, and then you recurse on, you call the same function again to work that. And in particular, we had that for lists. Because a list is a recursively defined structure. A list of students is a student plus a list of students, or it's empty. It's empty, or it's a student plus a list of students. And so we wrote a program that looked like that. Is the list empty? Otherwise, do something to the first one and something to the rest. That was a pattern we had. And whenever we processed a list, pretty much, that's what our program looked like. It was a pattern. So you could, by the time you got to the end of 150, if you had a list processing program, that template, you could write it down in your sleep, couldn't you? It's a pattern. We're going to look at how you take those patterns and make them concrete, make them part of the language. So we're going to have powerful patterns, which we can call abstractions, which are ways of writing programs. And that is going to give us cool ways to generalize programs. And those ways of generalizing programs will not just be the applications of patterns, but there may be some other things that we do, which we'll see this week and next. We'll start to see these patterns where we can create a particularly general program. For instance, what we're going to do this week and next week is we're going to go from trying to calculate the square root of a number to producing a function that will solve any equation. Any equation you like, whatever the equation is, whatever the expressions are involved in the equation, we can solve it, provided only that we can calculate the function. So we're going to move from one example, then we're going to produce a really powerful generalization. Probably we will do that next week. Okay, good. So that's what this course is going to be about. Now, lots of these things don't work or don't work very easily in languages like Java or C or whatever. And what we will be doing in 314 next term and next year is looking at how all this works. We're going to be looking at the structure and interpretation of computer programs as users of a computer programming language like Racket, that is a smart language like Racket, a powerful language like Racket this term. Next term, we will see how those smart languages work. What's behind the works? We will look at the program that makes that programming language work, because a programming language is itself a program which takes in other programs, evaluates them, and produces a result. Okay. Now, the practicalities of the course, you'll be glad to hear that this, if you want to be really cool, you have to fork out $70 or so to get the book, but thankfully, because the authors are from MIT, and MIT is very fond of the principle of open education, if you just Google for SICP, it's online. And if you use wget with the appropriate flags, you can put it on your computer, and I have it. I have the SICP on my computer, bookmarked in the toolbar of Mozilla, so that I can go straight to SICP any time I want. I'm not sure that MIT will be particularly pleased about you doing that, but if you just keep it on your own computer, it's just like caching it, so I don't think it's probably a very terrible thing for you to do. So you can doubly get it to your computer. You've got SICP. Right. That's important because sometimes when I'm asking you to do, I will be asking you to read the book section by section. I will be asking you to do the exercises in the book, and then I'm not going to write the exercises out again. Only if I want to give you an original exercise of mine will I write it out. I'll just say do exercise 4.3.17 in SICP. So you need to have the book, either you need to get a copy of it or you need to have it online on your computer. And of course, once I've asked you to do exercises, as you very well know, in any course given by me, there will be quizzes. There will be quizzes. These quizzes will constitute an important part of the evaluation for the course. That means you need to turn up. You need to turn up to take the quizzes, and you need to turn up to the classes. Not just the lectures, you need to turn up to the classes as well, because sometimes we will be doing evaluation in the classes too. So you need to turn up to the classes to get the best out of the course and to get a good grade. Right, okay. Is all this stuff important? Well, it's very important, and it makes a great deal of difference, and there have been some very important applications of it. One example is, firstly, if you want to get a job at Google, you should have read the Purple Book. That's definitely the case. People who haven't read read the purple book are not going to find it very easy to get a job at Google or a high-tech company like that. Secondly, for the last 6 years or so, Google have used very intensively one of the important ideas that was in SICP from 1989, which is now, and it was applied 15 years later by Google in 2004. They took this idea of powerful abstract ideas about how to program and making that a program itself, and they changed the whole of Google's infrastructure to work with an engine that they called MapReduce. Actually, they're just moving away from it now, but it's been running Google for the last 6 years. And if you read, there's a paper you can find you can Google for that as well, from Google Labs about MapReduce, in which they explicitly say, we're moving to MapReduce, which is a way of uniform way of processing very large quantities of data spread over lots and lots of computers, which is what Google has to do. We modeled MapReduce on ideas from functional programming, ideas from things like the purple book, which is what you have a model which says, what we do with data is we take a big piece of data like this and we map it, that is, we transform it into another piece of data of the same size, but it's had something done to it, or we reduce it, that is, we take the data and squidge it up. And then what Google did was to write an engine that did these two jobs for whatever it was you wanted to do, but did all the bookkeeping to make sure you could spread this job out over tens of thousands of different computers, so that anyone who wanted to write a program that did anything of this sort could always use the MapReduce engine and didn't need to worry about how the job was distributed, about getting all the results back again, and so on. It gave them an interface. They're moving it away from it now for different reasons, but it's been running Google for the last 6 years, so it's important. Okay, right. What do programs mean? Let's start looking at programs. Now, you should all be familiar with Racket, which was called Scheme when you encountered it, but it's now called Racket. And so we can look at the simplest possible program. Something like this. This is a very simple Racket program. What do we do to evaluate this? This is a piece of text, isn't it? And we can think of it looks like a list, doesn't it? It looks like a Racket list. It is a Racket list. It is processed by a program which processes lists. And what does the program do? It says, find out the value of each of these. There's a question mark there, isn't it? What do we mean by find out the values? And then take this one as a function and apply it to all of these, however many of them there are. Okay, so you evaluate each of these and then apply. And you think about this one. Same value, isn't it? And then you understand what we mean by evaluate. We mean if you've got one of these, another list, you do the same process recursively. So immediately in your mind, you can see a way you could write a program to do this evaluation. And we may even have done it with you, I think, at some point in 150. What you do is you look at something and say, is it a number? Okay, its value is the number. Is it a list? Do the process recursively. If it's a symbol like this, look up the function. Find the function which belongs to this, and then when we want to, we can apply the function. So the first thing we can see is we've got a process of evaluating expressions recursively. The nice thing about Racket expressions is that they transform very simply into data structures. If you look at other programming languages, then that transformation is not easy. It's complicated. But here, all you need to do is put a quote in front of it in Racket, and it's become a list. Okay, so that is a list. It's a list consisting of plus, 3, and the list consisting of plus 2 and 2. This is a list. We can process it like a list, and that's how we interpret those things. So the idea that we can interpret this, and we can write a program that does this. We can write a program which simply takes a program like this, a simple program, and evaluates it and does it correctly. And so we would need to look and see, is this a plus? If so, add these together. Is this a star? In which case, multiply these together. If this is a minus sign, then subtract one from the other. If it's a division, then divide one by the other. We can actually write a program which evaluates this program. Now that leaves the question about how the program that we wrote is evaluated, but at least we can see what's going on here. There is a simple recursive process, and this is a recursively defined data structure. We can say that what is this program? This program is either a number, or it's a list in this form, some operator, plus, minus, subtraction, division, followed by two programs. Right? And you see the program may be a number, or it may be another more complicated program. That's a recursive definition of that, and that's a program. Okay? And so we can understand quite clearly how those expressions are evaluated. We don't have a problem there about the meaning of that. Okay, good. What else do we have of importance? Well, the next thing we need is we need to explore the idea of a function. Now, we just kind of assumed this idea, didn't we? Right up to now, we've looked at functions, we've looked at methods in Java, and we've just said, we've had a kind of hand-waving feel about what was going on. And we've made some assumptions which are not always true about how functions are evaluated as well, which we're going to explore, because now the world is going to open up and we're going to see, it doesn't actually always have to be that way. So let's think, what do we mean when we define a function? What's going on? Well, first of all, let's look what it means when we define a name. We can do this. What this does is it creates a name somewhere, and when we subsequently refer to this name, we get a 3. Okay, fine. And there's something very special about that. That name is valid almost everywhere. And we're going to have to think about where does it have the meaning 3? Where might the name A not have the meaning 3 when we're writing a racket program? Where could you have written a racket program in the first year where there would be an A in the program? I mean, this define A3 appears at the front of the program, but there's an A somewhere in the program that doesn't mean 3. This will be our first example of names meaning different things in different places in the program. Can you construct a part of a program following on from define A3 in which A doesn't necessarily mean 3? Now, what was I going to do next? I was going to define a function. How can I define a function so that there's a piece of the program in which A doesn't necessarily mean 3? Yep?
If the parameter name is A.
Okay, I can write something like this. Fine, I can write a function. This is a function definition. Now, a function definition does two things, doesn't it? First of all, it defines this name square. And what is the meaning, what is the value of square? The value of square is this function itself. The value of square is something which encompasses the idea that there is a name A, and what we do when we get A is we multiply it by itself. And now, if I write down here, we're going to be clear, aren't we? That A is not always 3. Because if I now carry out this program, evaluate this program, the answer is not going to be 9. The answer is going to be 49. This definition of A does not apply in here. Okay? This is a different A from this A. So this is a process we've got to explore. We've got to understand that this A is different from this A. I mean, we didn't have to think about it very much before. Maybe a lot of the time we made sure that we didn't use the same name again in this way. But actually we can, and sometimes almost we're going to be forced to. So we need to think about that. So let's think about what it means. The next thing we need to do is think about what this means. How do we evaluate this? How do we give this a meaning when we've made this definition here? What's the process? So we can talk about this. This is what SICP calls it. You've got some things in here. What do we do? Of course, we need to say, what does that mean? Apply the first to the rest. We've got an instinctive idea what it means. What does it mean? Why do we all know, don't we, if we write square 7, that we're going to get the answer 49. That's better. How do we reach that? How do we reach that process? What's going on here between these two lines here that says we're going to get 49? What convinces you that when I write square 7, I'm going to get 49? What do? You look at this definition, don't you, to see what it's going to do. It happens we've given the definition a suitable name. What are we going to do there? What do we do when we evaluate a function? Well, we're applying square to 7. What we do is we say, we take this, and look here at the body of this function, and wherever we see an A, we will write 7. Right? And we will end up with star 7, 7. Well, we know how to do star 7, 7. Once we've got the letters out of this, we need to... So what does this mean? Okay. This is the formal parameter. Sorry. Didn't see what I was doing there. The formal parameter is this letter here, which is just a placeholder. It says, When we apply this function, wherever we see this in here, we're going to perform the substitution. That's why it's called a formal parameter. And this is an actual parameter. So, like all of the things we do in this process, we've written this, and almost as soon as we've written it, we're going to keep saying, but that's not quite right. Or it doesn't actually have to be exactly that way. But this will do as a first attempt at a definition of what we're doing. We evaluate all the parts of the combination, and that means what we're going to have done. For instance, if we're looking at just a tiny racket that's just got numbers and functions in it and doesn't have any other data types in it, that we will have reduced all of these to numbers, and then we take each of these numbers and poke that number into the function, into the body of the function, and then we will then have an expression which only involves, which we can evaluate recursively. So even if this has got more complicated expressions in it, we can still, even if this may have another function application of a named function, we can still carry out that process. So let's look, for instance, at an example of carrying that. That's a slightly more complicated program than square 7. So we can write the program. This program. Now let's think about the rules that we've said so far for this, say, how are we going to evaluate this? We need to evaluate this by finding the value of each part of the list and then applying the first one to the rest. So we find the value of this, that's the function square. We find the value, how do we find the value of this? What's it going to be? What's plus 4, 3? 7, yes. Okay, so we can look at the transformation process. It says, while we're evaluating this, we're going to produce, and then we'll do the substitution, and we get 49. Because we take 7 and substitute for all the a's in the body of the function. Okay, good. Did we have to do it that way? In other words, is that really the way we have to do it? We could do it another way. Actually, to give this process in full, we should produce. Okay? After we've done the substitution. That's to show the substitution taking place before the calculation. Right, that's another way. Now let's look at another way of doing it. Suppose we say, instead of saying the parts, evaluate the first part of the combination. All right, so we evaluate this. We find that this is the function square. What do we now do? Well, we've got a function, and we'll now apply the function to this, and we'll perform this substitution. So what are we then going to get? If I substitute the whole of this expression for the a in the definition of the function square, what am I going to get? That's right. We're going to get multiply plus 4, 3 plus 4, 3. Something different is happening. Now, we're still using substitution. In other words, our idea that you evaluate a function by performing this substitution for the for the names in the function, a process which we will find is not as simple as it seems, and now we get this, but this is an arithmetic expression that we can evaluate in the normal way. There's no more substitution to be done. What do? Well, we calculate these, don't we? So we can, the interesting thing is that what we get is times 7, 7. After doing this calculation, and then of course, we get to 49. Okay. Obviously we've got to the same answer, haven't we? We've got to the same answer, but we've got to it through a different route. What's the difference, the essential difference between these two ways of doing it? This has taken longer, hasn't it? It's because we've done the addition twice. We've done the addition twice. Interestingly, this way can sometimes be longer. You wouldn't think it. This way can sometimes be so much longer than this way, and we'll see that probably in the second hour. It's infinitely longer than that way. Okay. Right. Okay, that's fine. Now, but supposing, if we wind back, and supposing what we were asking was this. Okay. Right, and we've got, you remember, A is defined to be 3. So what are we going to do? What will we get here? What will this be? Remember, we've got, unfortunately I've made a mistake and rubbed those off. Define A3. So if I ask for square plus A3, 6. Okay. What's going to happen here? No, it's still going to work okay, isn't it? You'll see there's going to be a confusion, though. It's going to be very confusing because we're going to be substituting in here for A plus A3. You need two variables to make it go wrong. Okay, but what we'll see is that if you have this way of doing substitution, then there's the risk. How can we make that go wrong? And we've got rid of the A's. Yes, what goes wrong is you do the substitution. Oh no, that's still going to work fine. That's still going to work fine. Okay, that's not a good example, but you'll see that there's something that can go wrong if you've got a name defined outside and you substitute it into a function. There's potentially something that can go wrong, and that's something that we're going to come back to. Okay. Right. Good. Okay. So we've got a model for function application, and we can see that there are two possible ways of doing it. There's a model of substitution, and there's a question about the order in which we do things. This way is called normal order. Why do we call it normal order? Because it's the way we don't normally do things. Right? It's normal in the sense of a different field of study. In the sense of the lambda calculus, this is normal. But you have to remember, normal order is the way we don't normally do things. Java doesn't normally do things that way. Nor does Racket normally. Okay? Not normal. And this is called applicative order. It's, function application. This is called applicative order. Okay, good. Let's look at something where the two things definitely go wrong, where they definitely give different results, normal order and applicative order. We have cons. And actually, as you know, in Racket, we also have if. So I want to write a function which behaves like the if in Racket, but I'm going to define it using cons. So let's do it. Help me. Define. Our if. How many things do you have after an if in Racket? 3. Okay, and we're going to define it using cons.
And below A, the condition is A.
Yeah.
The result is B. And else C.
Anyone not understand that? Well, it's straightforward. We've defined our if statement. Okay. Now, let's look at a perfectly straightforward program, and we'll write it up on the board and then we'll run it after the break. So you'll have the break to think about it. If you do any thinking in the break. One of our standard favourite programs. Define. Fact end, and we're going to do it using if, except we're going to use our if. Using if, what does a factorial look like? Standard recursive definition of a factorial. Okay. Come on, let's engineer this properly. Okay? No, there's no else in an if statement.
Plus n, minus n, 1. No, this is 1, result is 1.
Yeah. What did you say?
Plus n, minus n.
Okay, criticize this program. You can, including you. What's wrong with that? What does it do?
There is another parenthesis after 1.
It's not factorial. It's picked up which side.
Huh?
It has
Not,
to multiply.
sorry, not plus. This is not plus, multiply.
Yes. First of all. Even now, just think about our recursive, you know, you can process numbers like you can process a list. And our classic how to design programs template says, what do we have? We do something in the trivial case, don't we? And then we do something which combines the head, which we can think of as this, with what? The head with the tail, or the head with
Tail applied to
the function applied to the tail? You've got it the other way around. In other words, you just need to go to our standard template for these kinds of programs to know that this is wrong. This can't be right. Because if you think about it, what do you ask for the factorial of 7. Is it 1? No, 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 no. This is 7 times 6. So the factorial of 7 is 42. Can't be right. Come on, you wrote it. What do we need to put here? What's wrong with this?
X and minus.
Ah, that's it. We need to, our template is that there's a recursive call, isn't there? Okay. Right. Now we've finally got this program right, but let's ask ourselves, and this is a question of evaluation order, does this program actually work? That's the question. Does this program actually work? So I'd like you to think about it, and then we'll find the answer after the break by typing it into the computer and trying it. So anyone who can figure the answer out before we get it into the computer, you'll get a small prize. I don't know what we'll give you some sort of small prize. So let's take a break now. So let's be back in 10 minutes. So that's about 8 minutes past. Let's try the program that we did. Did anyone come up with the answer in the break? No? Let's try our favourite basic recursive program, the factorial program. And we're going to look at this function. Always in the how to design programs world, we always use cons, not if. But we're going to be playing with if a bit in this. So it's going to be A, B, else C. And just let's see if this program, this function that we've written, appears to work. So we can write our if equals 1, 2, 8, 9. What should the answer be? Yep. Or if we ask it equals 1, 1, what should the answer be? 8. Seems like a working if statement, isn't it? Because if we do the same thing with if, we get the same answers. So our new if, which is our hyphen if, seems to work okay. Right, so that's our function, our if. Now let's do our factorial function. We finally managed to get this right, didn't we? Now that's a factorial using the standard if. Now let's do it again. Always remember to change the recursive call as well, otherwise it doesn't work. Right. Okay. So we've got a standard factorial function working with the standard if. We've got our factorial function working with our if. So let's just make sure that the factorial works. Seems to work okay. I mean, I'm not make sure. Test it for just a couple of values. Okay, fact1 should be 1. Fact 7 should be 5040. That looks okay, doesn't it? Good. Right, now let's look at our fact. Right, look at our fact 1. It's running. It's running, look. It's flashing on and off. Fortunately, it's not using up memory, but it's running, look. What's it doing? And it's not something, it's not like it's a very big number. We've asked it for the factorial of 1. You know, it should just come straight out, isn't it? Why? What's going wrong? What's going wrong? It's obviously something to do with order. Otherwise I wouldn't be showing this to you, would I? It's using up so much processor time that the mouse isn't responding properly. Let me give it a try and click a few times. Eventually it'll see that I've pressed stop and it'll stop. But let's think, what's going wrong? I've asked for the factorial of 1 in this function. You need to look at the rules for evaluation. Now, what do we say for the rule for the applicative order evaluation of a function? And our if is a function. And perhaps the thing you need to know is that if is not a function, it's something else. Our if is a function. So what do we do? What's the rule that tells us how we evaluate this? What did we say? We've rubbed it off. The rule says to evaluate an expression like this, come on, are we getting there? We need to evaluate each of the parts and then apply the first one to the rest. Okay. Still hasn't noticed I've clicked stop. Shall I try again? Looks like it. Yes, that's it. Do we want to go? Yes, certainly we do. The program ran out of memory. Kill. Right. What happened here? How can we evaluate? Let's consider evaluating this. Let's trace it. Our fact 1. Okay, it should be simple. It should just drop out, isn't it, with a 1. We're trying to calculate the factorial of 1. But the program used up all the memory and why? What did the rule said? And what we need to do is look at the rule, the evaluation rule. That's what tells us the meaning of this program. And the meaning of this program is different from the meaning of that program. Because part of the meaning of the program is the order in which it's evaluated in some circumstances. So if we evaluate if, how do we evaluate an if statement? You know, just tell me in words how you'd evaluate it. What do you think of the if statement as doing? Just in words, say what it does. Well, it looks at the condition, doesn't it? Yes, it looks at the condition. You have to get away from one-word answers. One-word answers just aren't going to work. Compare. Rabbit. One-word answers don't work. Okay? It looks at the condition. I mean, we might have just written true here. We can write any expression which evaluates to a truth value can go here, can't it? So we look at this value and then we choose to evaluate one of these two, don't we? But what does our if do? It doesn't exactly do that. It's a function. So what was the rule that I wrote on the board? Maybe some of you have copied it into your notes. What did we say? In applicative order, what do? We evaluate all of the things in the combination and then apply the function to the values. Okay, so we evaluate everything in this list. Right? And there are 3 things in this list, aren't there? So eventually, before we feed A, B and C into our if, we have to have found out what their values are. Okay? And what are the 3 things? That's easy. Less than or equal to 1, 1 is true. 1 is easy. It's 1. What's the value of this? How do we find the value of this? Well, we multiply n by our fact minus n1. So that's our fact of applied to 0. Okay? So we try and evaluate our fact 0, our if. This is true. This is 1. This is 0 times our fact minus 1. How do we find our fact minus 1? And that's what it was doing. Why does this go wrong when this doesn't? This goes wrong. You see, it goes, evaluates that, because it needs to evaluate all of these before it can apply the function. That's applicative order. It evaluates all its parameters first. What does this do? It evaluates this one, and then according to the value of this one, decides whether to evaluate this one or this one. Right? That's the difference. This is not applicative order. Applicative order would mean finding the value of this first. And of course, finding the value of this first involves the recursion. And finding the value of that involves recursion. And finding the value of that involves recursion. And finding the value of that involves recursion. That's why it went on forever and ran out of memory. So what we find is that evaluation order can make a difference to whether or not a program goes into a loop. In particular, when you have a function which throws away one of its parameters. In other words, if you have a parameter whose evaluation goes into a loop, but your function throws it away, then it's important whether or not you try to evaluate the parameter before you substitute it, or you substitute it before you evaluate it. Because if you substitute before you evaluate it, you don't get into the loop. Okay, so that makes the difference. Now, if you don't believe me, you should take these programs and you should put them on your computer and try them out. It's actually one of the exercises in SICP is to try this and then try to explain why it's happening. And the important thing is this. That's why I said, we said that normal order, it did the plus 4, 3 twice. It takes longer. Sometimes applicative order takes longer. In fact, it takes infinitely longer because it doesn't terminate. Okay, so this is our first example where looking at the meanings of programs, we find that it's not quite obvious. That there are different ways of evaluation. In fact, what you can do in Scheme, and by doing this you can see that this program is essentially correct, that is the our fact program is essentially correct, we can switch to a different variant of racket called lazy racket. And lazy racket is smart but lazy. Someone wrote that on the board before the lesson started. It's smart but lazy. So what does lazy racket does, it takes all the functions and amongst other things, make them work in normal order instead of applicative order. It changes the way in which the language works. It's a different version of racket, lazy racket, in which the application of functions is in normal order. So that what happens is the substitution is done first. It doesn't actually work that way, but it's something like that. The substitution is done first and the evaluation is done afterwards. So if I change this up here, make it lazy, right? And what do I get? It works. I've made the language lazy. I haven't changed the program at all. So this program gives, and of course I can try it for a real factorial. Or that's going to be a nice big number, isn't it? That'll take a little time to calculate, but because it's a very big number. There we are. No? But it doesn't go into a loop. Why does a factorial have so many noughts on the end? Why does a factorial have so many noughts on the end? I'm just going to put this on. This one takes a long time to put on silent. Why does a factorial have so many noughts on the end? Come on, I'm waiting for an answer. Yeah, that's on silent. Good. I'll put this one on silent. Forgot to do it before I came in. Newer model Nokia, it's quicker. Why does it have so many noughts on the end? The number was 7777. Why does a factorial have so many noughts on the end? Are you thinking? Well, what is 7777 factorial? It's 7777977776 times 77775 times 77774. Why does it have so many noughts on the end? Think about it. How do the noughts get there? You can scroll up and see how big a number it is. Oh, lots of noughts, right? And then there's all these other numbers. It's really a seriously big number, isn't it? 7,700. But it came out quite quickly. Why does it have so many noughts on the end? Well, if you think about it, yep.
When you multiply a number that ends with a 0 with another number, there is a chance that the zeros increase or stay the same, but 0 will not disappear. And through the big multiplication and all those tens and hundreds, you'll get this many zeros.
Yeah, okay, it's not the case that when you multiply a number that ends in a naught by another number that the number of noughts can stay the same. The number of noughts always increases. So with 7,000, you've got 700 numbers with a naught on the end, right? In the multiplication. So you're going to get 700 zeros just from the ones that end in dot. You've also got another 700 numbers that end with 5, and more than 700 that end in an even number. So that's another 700 zeros. That's 1,400 zeros. I think that's enough. There should be about 1,400 zeros there. That's why it's got so many zeros. Okay, so what we've seen there is we've seen that evaluation order is important. Okay, and we'll keep coming back to that. Right, now let's look at another question. We're going to look at a kind of program, and we're going to look at a specific problem, and then we're going to start generalizing it. And we're going to see how we can, by generalizing it, we can come to some understanding of a different kind of thing about the structure of programs. Why we use functions and why we use them in the way that we do. I remember going around to see a friend of Phyllis's whose son was 10 years old. He was very excited when he heard that I was coming, because he knew I was a mathematician. And he said, when I came, he said, "Are you a mathematician?" I said, "Yes." He says, "How do you calculate a square root? How do you calculate the square root of a number?" And I didn't ask, but it was perfectly obvious to me that he'd asked this question at school, and the teacher had said, not been able to give him the answer and said something else. "So why are you interested in that? Get on with your homework," He was obviously determined to find out how you calculate a square root. Right. Well, there you are. It's a button you have on the... Every calculator has a square root button on it, doesn't it? I don't know why. You know, you have addition, subtraction, multiplication, division, and square root. But I don't think, you know, I've never come across an accountant, for instance, using square roots. The only reason the square root button is there is because it's easy to put into the calculator. You know, it's strange. You're on a basic calculator, you have square root, but you don't have sine and cosine. Very interesting. But how do you calculate a square root? How do we calculate the square root of 7? Any ideas?
There is a method Newton's method.
Yes, that's right. Newton's method. What is Newton's method?
I only read it.
Ah, poor old Newton. 350 years in the ground, and no, not 300 years in the ground probably. And his method has been forgotten. Okay, there is a method called Newton's method. Any idea what sort of method this is? I'm sure you did it at school. It's some kind of a limit, isn't it? It's some kind of, it's not a limit. A limit is a mathematical thing, right? And it's precise. And so, you know, because all the limits are like this, aren't they? When you writing maths, you write lim, n goes to infinity, and then you write something here, don't you? We haven't got time for that, right? That's too long, infinity. What we're interested in computing, obviously this is a theoretical concept, but we can't actually do it. We can't actually do that process of going to infinity. In fact, there's another reason why we can't do that in a computer. Why can't we calculate the square root, you know, just exactly? Why can't we calculate? I mean, we can, except for things which have integer square roots. Why can't we calculate the square root of 7 in a computer exactly? It can't be divided by 2? You're kind of on the right track.
Because it's not exact.
The square root of 7 is perfectly exact. It's that number which you multiply, which when you multiply it by itself makes 7.
And memory constraints.
Memory constraints. We're kind of getting there.
It's not power of 2.
Huh?
It's not power.
It's not powerful.
Power of 2.
You're kind of getting there. I mean, I can represent 7. 7 isn't the power of 2. That's perfect. I can calculate 7, or I can calculate 7 divided by 2. That's not a power of 2 either. I can calculate lots of numbers that are not a power of 2. What's the important thing about the square root of 7? That means I can't have it. I can't even store it in a computer. I wonder why we bother teaching you math, because you just forget it all. What is it about the square root of 7? You prove it in first year calculus. The square root of 7 is a particular kind of number. Prime.
7 is prime.
Primes have to be integers. The square root of 7 is not an integer. Well, what's the property of the square root of 7 that means you can't represent it exactly in a computer? It's irrational. It's not a rational number. You can't, you know, it's irrational, so you can't write it down even. Because it doesn't, you know, because if it was rational, it would finish or repeat as a decimal number. But it's not. It just goes on and on and on and on and on. So what we have to do with square roots is we have to calculate a number that's close to the square root. An approximation for the square root. That's all we can ever actually write down or store in a computer. An approximation for the square root. Okay, good. How do we do it? what we want to do, a process of approximation is we need some kind of process which we start somewhere, it's like a limit, and we gradually get closer to the square root. Okay, that's what we're going to do. We're going to go something like this. Get close to the square root. How can we do that? What's Newton's method? Because we're going to find that Newton's method, we can generalize it later. We start with working on the square root. We're not going to finish it today, plainly. We'll start working on how to calculate a square root, and then we'll move on to a generalization of Newton's method that will enable us to solve any equation in about 8 lines of code. Right. If I asked you with pencil and paper or with a calculator to find the square root of 7, a calculator without the square root key on it, of course, how would you go about it? Can you guess the square root of 7? What sort of number must it be? Roughly.
Between 2 and 3.
It must be between 2 and 3. Very good. Why must it be between 2 and 3?
Because 4 and 9 is the...
Yeah, so because 7 is between 4 and 9, so the square root of 7 must be between 2 and 3. Okay, so, and 2 is obviously less than the square root, and 3 is greater than the square root. So can you think of a number which must be closer to the square root than 2 or 3 is? If 2 is less than the square root, and 3 is greater than the square root, then there's a number that must be closer to the square root than one of them is, to be more accurate. 2.5. Take the middle. Okay? 2.5. And what could we do with 2.5? We can find out, can't we, if 2.5... We could find out if 2.5 was... What's the square of 2.5? It's 625. So that's less. So then we could take 2.5 and 3 are on opposite sides of the square root, aren't we? We could take... well, let's try 2.75. Right? And so by a process of halving, we could get there, couldn't we? That's one way of getting to the square root. That's not Newton's method, though. The idea here is that we're finding a value which is above the square root, a value below the square root, and taking the one in the middle. Right? And then we're repeating the process of finding a value below, a value above, taking the one in the middle. Value below, and as long as the gap is getting smaller all the time, it may be getting smaller slowly or quickly, what happens is we're going to close in on the square root, and then when our two guesses are close enough together, in other words, we've got the number 2.734 and 2.735. One is greater than the square root of 7 because we square it and find out that it is greater than 7, and one is less than the square root of 7. There's, oh, that's good enough. It's 2.7345. Okay, we'll take the middle and we'll accept it. Now Newton's method isn't quite like that because Newton's method only starts with a single guess. So, let's call our number k. Now we've got to guess. We've guessed that the square root of 7 is 2.5. Okay? How can we get to a number which we definitely know will be greater than the square root of 7? Well, one way we could do is we could divide this number into k. So k divided by g So if g is less than the square root of k, and we divide g into k, then k divided by g will be more than the square root of k. If g, our guess, is greater than the square root of k, if we divide g into k, then this number will be smaller than the square root of k. So we've got we've got a definite way of getting two numbers, one on either side. We've got one number on either side of the square root. Now let's take the middle one of those. The average. So that's half g plus k of g. Okay? And again. Try it again. When are we going to stop? This is fine. This is just going to keep getting numbers that are closer and closer and closer. If you think about it, this number, what you've got is you've got a nice balance across the square root, and the number that is in the middle, actually, if you do the calculation, is bound to be closer than either of these was to the square root. And so you're going to get a thing that's going to close in on the square root. What I just said, of course, is untrue. I'll leave you to find out the circumstances in which it isn't true. Maybe we'll set you that as a question for next week. Do it again until close enough. One of the ways we can tell we are close enough, we can look at the distance between these two. And if the distance between those is less than our limit, say our limit's 0.0000001, then we know the square root can't be further away than that, because the square root's somewhere in between. So we know we're very close to the square root, and we can say in advance how accurate we want it to be. Now what we want to do to write this program is to think about this as a process. And this is in terms of how to design programs. This is generative recursion, isn't it? What we're doing is we're taking a problem and we're producing a smaller problem and a smaller problem and a smaller problem. And we get to some point where we have a termination condition, and then we say it's the trivial case. What's the trivial case? The trivial case is in which these two are so close together that we're not bothered about them. Okay. And what's the process we've got going on here? We've got two processes going on. One is getting a better guess. You see, we're taking this as our new guess. It's getting a better guess. And we've got another process that says, is our guess good enough? Okay, so we can even make a draft of our program. Let's just see if I can. That's it. We can kind of draft a program, and we can think of our program in this way. Let's call it k to be. Oh, what we need a square root of k. Ah, and we need a guess, don't we? So this looks like, and guess is going to keep getting closer and closer. It kind of looks like an accumulator program for HTTP, because this is an accumulator. This is the accumulator. It's getting closer and closer to the value. So we could say for our program something like this. A template, cond. I didn't want to write it. I'm sorry, I'm not thinking. The reason I've written it like this is that what I'm trying to do here is trying to write this program in a modular way so that we can see the structure of what we're doing. In other words, what we're doing is we're saying, well, there's something to get a better guess. There's something going on here. The idea, the general idea is getting a better guess. What I started to do here was to write in a specific way of getting a better guess. Instead of doing that, what I've done is I've said, I'll think about that later. I'll write a program which gets me a better guess. In the same way, I've said there's some criterion for being good enough. I say, I don't want to think about that now. I'm not going to put that in this program. I'm going to have some other function which defines what's good enough. And of course, what I can write here, instead of the dots, is k. If it's good enough, if k is good enough, sorry, guess. It's late in the afternoon. Guess. If the guess is good enough, then it's good enough and we can use it. Otherwise, we're going to take the square root of k, starting with a better guess. And we're going to use a better guess made from k and guess. Then those functions become really easy to write. From these definitions here, so we can define and now we're going to write what I was about to write over there. Plus guess divide k guess whole thing divided by 2. That's a better guess. And I can make a criterion for good enough. Define well, quite simply, what we're going to want to say is it close enough? Is the difference between the square of our guess and k small enough? So we can say something like this. Less than. One. What's wrong with that? We've done these sorts of programs before. You should be... That program doesn't work. See if you're awake. What's wrong with that program? That program will very, very quickly give you an absolutely wrong answer that's miles away from the square root. No, the difference needs to be smaller than some small figure, and I've picked a small figure out of the air there, 0.0000001. It certainly needs to be less than. Huh? You're on the road, you say k and guess could be the wrong way round. It should be the other way around. Minus guess k. Is that what you're saying?
No,
definition we said k and then guess, but in the square root function.
Ah, you are right, actually, it should be. Yes, you're right, but it still doesn't work. It is late in the afternoon. Right. Okay, that was right. The program's still shit. Sorry, wrong. The program's still wrong. It was wronger than I thought. That was unintentionally wrong. This is intentionally wrong. This is intentionally wrong. The other mistake was unintentional. Shouldn't try to do these things at...
Square root guess is larger than k program.
That's it. You see, I mean, I can put in a guess for the square root of 7 of 1,000,000. Okay? 1,000,000 times 1,000,000 is 1,000,000,000,000. Okay, it's 1,000,000,000,000. But minus 7 minus 1,000,000,000,000 is less than 0.001 because it's a very large negative number. Okay, so you've got my intentional error now. You've got my unintentional error. The intentional. So how do I make this work properly? We want this to fail if this is a very large negative number. We want the size of this to be small, don't we? Has everyone understood what the problem is? If this is, guess is 1,000,000. You take 1,000,000 away from 7, and you've guessed that the square root of 7 is 1,000,000, and you take this away from 7, you get a very large negative number. And this very large negative number is less than 0.00001 because 0.00001 is a positive number. And all the negative numbers are less than any positive number. What we want is the size of this to be smaller than that. Yep? Absolutely. And we need to take the absolute value of it. Okay? Right. Now what we've achieved here, and we're going to finish here, is that we have a particular process which is Newton's method for finding a square root. Have you found something else? But what we've done is we've put the details of the method here, and we've said, look, actually there's nothing here really that's about square root. This is about a general method for finding an approximation, isn't it? We're saying if our guess is good enough, then the guess is okay. And if it's not, then do the process again with something where we've made a better guess. Okay. So what we've done here is by extracting these functions, good enough and better guess, okay, we have generalized. This is generalized. So can you see what you might want to do? You could say this is a general approximating program, isn't it? What we're saying is we've got something with some parameters and we've got a guess. And what we want to do is we say, is the guess good enough? Okay, we're finished. If the guess is not good enough, let's find a better guess. So can you see what we might want to do with these things? Good enough and better guess. We can make this is a general process for finding, for approximating to something and for finding a close value to the value that we're looking for. What might we want to do with this? Well, what do we do when we have processes when we have patterns like this before in the first year? We keep doing the same thing over and over again. We keep writing the same program. We write all these list programs over and over again. A program which takes the list and transforms it into another list. So we write a program that multiplies every number in the list by 2. We write another program that squares every number in the list. We write a program that adds 3 to every number in the list. And we look at them, and what do we see? There's something common going on. isn't there? There's a pattern. What can we do with these to express this pattern? To generalize it. How do we generalize something? We make a function. We generalize squaring, times 4, 4, times 7, 7, and we say times XX. And we make x a parameter, yes?
We make our function a higher order function and feed it to functions.
That's right. We put this up here. And this up here. What we've now done is we've said the functions good enough and better guess can be parameters of this function. Now you see that the meaning of these has suddenly changed. Good enough now doesn't necessarily mean this good enough. It could be any old good enough. Right? We can slot in any good enough, which takes 2 parameters. Better guess doesn't have to be this way of finding a better guess. It could be another way of finding a better guess. Maybe we'll find a better way. So better guess and good enough have now become parameters, so we've generalized the function. Okay, and we're going to go further with this idea next week. So I'll set you some examples in the next day or so. We'll be up on Moodle for you to work on. And I will see you on Thursday, where we'll be doing a completely different track. We'll be looking at a completely different programming language. So Thursdays will be on a different track, which I hope will run in parallel with this track. So we'll be coming back to this subject next Tuesday.